Welcome to Lesson 12, Mechanical Vibrations. We will look at spring mass systems with no external forces, a spring hooked to a mass. We will consider undamped, underdamped, critically damped, and overdamped systems. Let's talk about mass versus weight. Newton's second law says that force equals mass times acceleration. Using common units, we have that a force of 1 Newton will accelerate a mass of 1 kilogram at 1 meter per second per second. A force of 1 pound will accelerate a mass of 1 slug at 1 foot per second per second. Notice that we are measuring forces either in newtons or pounds. Those are two commonly used units for force. We'll measure masses in kilograms or slugs and accelerations in meters per second or feet per second. The weight of an object is the force due to gravity on that object. Mass is a property of a body, does not depend on its environment. Its weight is due to gravity. For instance, on Earth, the acceleration due to gravity is approximately 32 feet per second at the surface of the Earth. So a force of 32 pounds will accelerate a mass of 1 slug at 32 feet per second. Just more or less multiplying this by 32 using force equals ma. A mass of 1 slug weighs on Earth about 32 pounds. And we can get this result about weight, the weight 32 pounds. Remember, we measure forces like weight is a force due to gravity. So a mass of 1 slug weighs about 32 pounds on Earth. If you went to Mars, we would have different results. Acceleration due to gravity on Earth also can be expressed as about 9.8 meters per second. So we can say that a force of 9.8 newtons will accelerate a mass of 1 kilogram at 9.8 meters per second. And so that tells us that a mass of 1 kilogram weighs on Earth about 9.8 newtons. So first let's look at undamped oscillations. Suppose you have a mass attached to a wall and a mass attached to the spring. Here's a diagram showing that. Here's the wall, here's the spring, and here is the mass attached to the spring. We'll let x of t be the position of the mass. In this case, I'll let x of t be the position of this side of the mass along a number line. So on the number line we have 0 somewhere. Let's say positive numbers off to the right this way, away from the wall. Negative numbers to the left of 0, starting there and going to the left. Okay, we'll assume that the position of the end of the spring at time t is given by x of t. X of 0 corresponds to the unstretched and compressed equilibrium point. For instance, in this figure, if the mass were right here so that the spring would go from here out to 0, that would be the equilibrium point. Hooke's law says that the spring exerts a restoring force, which we'll call F sub s, and it depends on the position of the mass, F sub s of x on the mass, by that restoring force is equal to minus k times x, where k is a constant called the spring constant. With undamped oscillations, we will assume that there are no other forces other than that by the spring constant. So there's no gravity taken into account and no drag of the mass through perhaps a fluid. So in that case, here's what we can say. Using force equals ma, first we can say that the force is equal to minus kx by Hooke's law. but the force, remember, is m times a, mass times acceleration. So here's the mass, second derivative of x with respect to t is the acceleration, equals minus kx, the force. Mass times acceleration equals the force. A negative sign here, because if x is positive, as it is in this diagram, the force is pointing in the negative direction. So we have this equation, and this equation holds whether x is positive or negative, whether the mass is over here or over here. Just rewriting this equation, we can write it as m times the second derivative of x with respect to t plus k times x equals 0. So this is the equation of motion for this situation where we have undamped oscillations. So let's suppose that we are looking at the undamped case, spring attached to a mass, and the spring is also attached to the wall. We saw that the equation of motion is this, m times second derivative of x with respect to time plus constant k times x equals 0. So this is a constant coefficient homogeneous ordinary differential equation. Its characteristic equation is mr squared plus k equals 0. And solving this for r, we get that if we subtract k from both sides, divide both sides by m, and then what we would have is r squared equals minus k divided by m. Take square roots, and we would get that r is plus or minus I times the square root of k over m. In that case, the general solution to this ordinary differential equation, using facts that we already know about homogeneous constant coefficient linear differential equations with complex roots to the characteristic equation, x of t is going to be some constant cosine square root of k over m times t plus another constant sine of square root of k over m times t. And we saw in a previous lesson that this can be written combined as a some amplitude cosine of the square root of k over m times t minus a phase shift alpha. This is undamped harmonic motion. There's no damping due to friction or drag. And so what happens here we see is that mass is just going to oscillate back and forth forever. If there's no damping, then the oscillations just continue with a constant amplitude at any particular interval of time. Let's look at this example. A spring is attached to a wall. A ball that weighs 2 pounds on earth is attached to the other end of that spring, and the spring has a spring constant of 3 pounds per foot. So if you stretch the spring 1 foot, there would be a restoring force of 3 pounds. The spring is stretched 1 foot from its equilibrium position and released with a speed of 2 feet per second towards the wall. Find x of t, the position of the end of the spring relative to the equilibrium position. Assume there is no friction nor gravity. So, the solution. First of all, since the ball weighs 2 pounds on earth, that mass is 2/32 of a slug. So m times the second derivative of x with respect to t plus k times x in this case is going to be 2/32 times that second derivative of x with respect to t plus the spring constant 3 times x equals 0. We are just plugging in the mass m and k into this equation. So the characteristic equation then for this differential equation is 2/32 r squared plus 3 equals 0. So 2/32 r squared equals minus 3. So r equals plus or minus the square root of minus 96 over 2. And that's the same as r equals plus or minus I times the square root of 48. So that tells us then that the general solution is x of t is some constant times cosine squared root of 48 times t plus another constant b times sine square root of 48 times t. These constants a and b will be determined by the initial conditions up here. So x of 0 then, by this formula, is a cosine 0 plus b sine 0. This just simplifies to a. And x of 0 is 1, so a has to equal 1. Differentiate this general solution to find x prime of t using the chain rule when necessary. So x prime of t is a times square root of 48 sine square root of 48 t plus b times square root of 48 cosine square root of 48 times t. Then x of 0, looking at the second initial condition, just plug in zeros for the t's and we get this. Sine of 0 is 0, cosine of 0 is 1. So this just simplifies to b times the square root of 48 times 1, which is b times the square root of 48. And according to this initial condition, x prime of 0 has to be minus 2. So that tells us then that b is minus 2 over the square root of 48. So plugging in the values of a and b into this formula up here, we get the solution to the initial value problem. X of t is cosine square root of 48 times t minus 2 over square root of 48 sine of square root of 48 times t. Let's continue this example further. Let's consider this problem. Let x of t equal cosine square root of 48 times t minus 2 over the square root of 48 sine square root of 48 times t. Let's find the amplitude and phase angle for the above curve and sketch the graph. So this basically was the motion of that mass on a spring that we considered earlier. First, let's compute the amplitude. We'll call it a. It's going to be the square root of 1 squared from the coefficient in front of the cosine plus this number squared. And so when you compute this, you'll find it's 1 over 24 times square root of 577, which is about 1.0009. So then multiplying this equation up here and dividing also by this amplitude, we can write x of t in this form. And then for the phase angle, we have that cosine of alpha is this number right here, and that simplifies to 24 over the square root of 577. The sine of alpha is this negative coefficient right here, and that simplifies to minus 4 square root of 3 over the square root of 577. The cosine of alpha is positive, the sine of alpha is negative, so that tells us our angle alpha is in the fourth quadrant. So we can compute alpha by noting that the tangent of alpha has to be sine of alpha over cosine of alpha, which simplifies to this. And so alpha is then going to be the inverse tangent of minus the square root of 3 over 6, which is about minus 0.28. We were able to do this last step because inverse tangents of numbers are between minus pi over 2 and pi over 2, which does cover the fourth quadrant. If our angle alpha were not in the first or fourth quadrants, we would have to take that into account. But in any case, we're okay right now. So x of t is approximately 1.0009, did I say too many zeros? I'm not sure, times cosine of the square root of 48 times t minus minus 0.28, which is plus 0.28. So this is a decimal approximation of the position of that mass at time t. As a prelude, let's talk about frequency, circular frequency, and period for a periodic function. As an example, suppose the electricity coming out of your U.S. home's outlet, electrical outlet, is about 120 volts root mean square at 60 cycles per second. 60 cycles per second is also called 60 hertz. 1 hertz is 1 cycle per second. This means, if you've studied root mean square voltages before, that the peak voltage is about 170 volts and the frequency F is 60 cycles per second. So that means that we could have, for instance, the voltage as a function of time measured in seconds equals 170 times cosine of 120 times pi times t. Now, if you think about this for a minute, if we let t be 1/60th of a second, here's what would happen during that 1/60th of a second in this graph here. The voltage would start at 170, it would decrease to minus 170, and then it would go back up to 170 at 1/60th of a second, which is about 0.0166 seconds. Here we're assuming that the phase angle is 0, but it could be something else. This graph could be shifted somewhere else so that it doesn't start right here at time t equals 0. So the instantaneous voltage is going to oscillate between about plus 170 and minus 170 volts. So if V of t equals a cosine omega t, then a is called the amplitude of the periodic function, this cosine function, and omega is called the circular frequency. So for a typical US house voltage, where V of t is about 170 cosine of 120 pi times t, the amplitude is 170 measured in volts, for instance, and omega is 120 pi radians per second. This V of t is a periodic function because there is a number t satisfying that for all numbers little t, V of little t plus capital T equals V of little t. The smallest capital T that satisfies this is called the principal period of this function. And often we'll just say period, meaning principal period. So we can say that the period for US voltage V of t is t equals 1/60th of a second. Here are some relationships that we need to know. First of all, the circular frequency omega is equal to 2 times pi times the frequency. So this equation relates circular frequency and frequency. The period of oscillation, capital T, is 1 over f, 1 over the frequency. As an example, let's look at US voltage. V of t is 170 cosine of omega t. The frequency of the voltage, we're told, was 60 cycles per second, so that tells us that f is 60. In that case, the circular frequency is 2 pi times 60, which is 120 pi. What does this circular frequency mean? Well, basically, what's going to happen is you're going to be going in a circle. And if you think of a unit circle, their circumference is going to be 2 pi. And what you're doing is going through 120 pi radians every second around that circle. So circular frequency is 120 pi, and not much more I can say about that. The period, capital T, is 1 over the frequency, and that's 1 over 60th seconds. Remember that the frequency was 60 cycles per second, and cycle really doesn't have a unit, isn't really a unit, so it's 60 per second. 1 over 60 per second is 1/60th of a second, bringing that division by seconds from the denominator out to the numerator as just a multiple of seconds. So V of t then is going to be 170 cosine 120 pi t. Let's go back to our example of the harmonic oscillator, a spring and mass system. We found that x of t is about 1.0009 times cosine of the square root of 48 times t plus 0.28. Let's consider the following problem. Find the frequency and circular frequency of the oscillation. Okay, well, we look at the equation here that we have for the position x as a function of time t, and we can think of it as x of t equals a cosine omega times t minus a phase angle alpha. And in our case, it's 1.009 times cosine square root of 48 times t plus 0.28. So the square root of 48 times t has to be omega t. So the omega has to be the square root of 48, which is just a little bit less than 7, I guess. Square root of 49 is 7. Well, since omega, the circular frequency, is 2 times pi times the frequency f, we have that omega, the square root of 48, equals 2 times pi times f. So solving this for f, let's divide both sides by 2 pi. F is equal to the square root of 48 divided by 2 pi, and if you punch that into a calculator, you'll find that that's approximately 1.1. Okay, so what have we found up here? The circular frequency omega is the square root of 48 radians per second, and the frequency is the square root of 48 over 2 pi, which is about 1.1 cycles per second, which is the same as 1.1 hertz. Okay, next problem. Let's find the period of this function. This function up here involving the cosine is a periodic function, so what is the period? Well, the period, remember, is going to be 1 over the frequency, and so this is just the reciprocal of the frequency, isn't it? We found that the frequency was square root of 48 over 2 pi, so 1 over f is going to be 2 pi divided by square root of 48, and that turns out to be approximately 0.907 seconds. Here is the graph of this function x of t, at least part of the graph, and if we look at the part of the graph between time t equals 0 and the time t equals 0.907, that part of the graph is shown in red here, and that's the graph of this function over one period, starting at 0 and ending at about 0.907 seconds. So now let's consider a damped harmonic oscillator. This model is going to have an extra term for fluid friction. The fluid could be air, or it could be oil, or something else. And we're going to assume that the fluid friction, the drag, is proportional to the velocity of the mass. So what we're going to have is another term in our model, a force due to drag, and it's going to be minus some constant of proportionality c times the velocity dx dt. So in this case, we can say that in this picture we have still the wall, we still have the spring here, the mass at the end of the spring. There's a restoring force due to the stretching or compression of the spring by Hooke's law, and we also have a velocity for this mass. It's going, let's say, in the positive direction in this picture at least, and the force due to drag is in the direction opposite to the velocity and is proportional to the velocity. Okay, so for this mass, the mass times its acceleration is equal to the total force on this mass, which in this case is equal to the restoring force due to the spring, Hooke's law, plus the force due to drag. So ma in this case is m times the second derivative of the position x with respect to time, and that equals the force due to the spring, which is minus kx, plus the force due to drag, which is minus c dx dt. Rearranging these terms, we can write the differential equation as m times the second derivative of x with respect to t plus c times the derivative of x with respect to t plus k times x equals 0. So there are 4 cases that we have to consider when we look at a spring and mass combination, and those 4 cases depend on damping. We saw that in general, the equation of motion in this case is given by this equation, and so its characteristic equation is this. It's an algebraic equation in R. It's a quadratic equation in R. Using the quadratic formula, we get that the solutions to this characteristic equation are R equals minus C plus or minus the square root of C squared minus 4mk divided by 2m. If C equals 0, then we really don't have any damping, and the solutions to this equation up here, mr squared plus k equals 0, are just going to be purely imaginary numbers, 0 plus or minus I times omega. So solutions to the ordinary differential equation, we've seen this sort of differential equation before. It was before we started looking at masses and springs, and we saw that the solution was x of t equals a constant cosine omega t plus another constant times sine omega t, and you get oscillations going on with constant magnitude forever. The second of the 4 cases, if C is positive, so you actually do have some damping, and C squared minus 4mk is negative, that means that C is small compared to 4mk. The system is underdamped. C is our damping constant, so that for small c, we will have underdamped system. The solutions to the characteristic equation in this case are R equals minus beta plus or minus I omega, and solutions to the ordinary differential equation in that case are e to the minus beta t times c1 cosine omega t plus c2 sine omega t, and we can combine these two together into one cosine term with a phase shift involved. So we can write this solution as some amplitude a times an exponential e to the minus beta t times cosine of omega t minus the phase angle alpha. In this case, the oscillations die out exponentially as t goes to infinity. Continuing to look at the 4 cases of damping, we're still looking at the same differential equation as before with the same characteristic equation, and the characteristic equation has solutions that look like this. By using the quadratic formula, we could find this. And C, remember, is this damping coefficient. The third possibility is if C is positive and C squared minus 4mk equals 0, that is when the system is called critically damped. In that case, this discriminant is going to be 0, so I just have minus c plus or minus the square root of 0 over 2m, and so that tells us that the solutions are going to be a double root, a root of multiplicity 2. R is minus c over 2m, and we'll call that minus beta, where beta is a positive number. So in that case, the solution to the differential equation looks like x of t equals a constant times e to the minus beta t plus another constant c sub 2 times t e to the minus beta t. This is purely involving exponential functions, and I guess a factor of t here. This has no oscillations whatsoever, and x of t will go to 0 as t goes to infinity because of these exponential factors that basically decay, get closer and closer to zero as t goes to infinity. The fourth situation is overdamping. If you still have a positive damping constant and c squared minus 4mk is greater than 0, then when you look up here, you're going to have the square root of a positive number here. In that case, the system is overdamped, and the characteristic equation has distinct real roots, which we'll call minus beta 1 and minus beta 2. Beta 1 and beta 2 are positive, so minus beta 1 and minus beta 2 are negative. In that case, the solution looks like x of t equals c1 e to the minus beta 1t plus c2 e to the minus beta 2 times t. Once again, we have no oscillations, and x of t does go to 0 as t goes to infinity. The motion dies out as t goes to infinity. So we still are looking at this equation of motion, and we're considering, recall, the underdamped case. The characteristic equation is this quadratic equation, and the solutions to that quadratic equation are r equals this stuff, minus c plus or minus the square root of this stuff over 2m. The discriminant is the stuff under this square root, c squared minus 2mk. The system is underdamped if that discriminant, c squared minus 4mk, is less than 0. In that case, we're going to have solutions r equals minus c over 2m plus or minus the square root of a negative number over 2m. So we can write that as r equals minus c over 2m plus or minus I times the square root of 4mk minus c squared over 4m squared. We took this negative number here, we multiplied by minus 1 to get 4mk minus c squared, and the 2m inside the square root becomes the square root of 4m squared in the denominator, and since this was the square root of a negative number, remember it's I times this square root. Let's call this minus beta plus or minus I times omega sub 1. So the characteristic equation in the underdamped system has two complex conjugate solutions. So in this system then, we saw that the general solution is this, and we can write it, this term plus this term, as the cosine of this stuff, including a phase shift alpha. And then if we call this stuff here minus beta times t, and if we call this square root, let's call it omega sub 1, this solution here has the form x of t equals an amplitude, let's call it for a minute, e to the minus beta t cosine omega sub 1 times t minus alpha. If you look at this, we do not really have a constant amplitude. The e to the minus beta t, when t equals 0, has value 1. And so you get a times 1 times cosine of something. But as t goes to infinity, this e to the minus beta t term goes to 0. And so what you have in this case are oscillations that die out as t goes to infinity. So what sort of motion do you have in the underdamped case? Let's look at a plot of x of t equals 3e to the minus half t cosine of 3 times t minus pi over 2. We have several graphs here, so let's see what's going on. Consider this 3e to the minus half t times 1. The graph of that would just be x equals 3e to the minus half t, which is shown here. If we look at minus that, x equals minus 3e to the minus half t, that's this curve right here. We would have these curves if this second factor here, sorry, were identically 1. But it's not. It's cosine 3t minus pi over 2. Cosine of something always is somewhere between minus 1 and 1. So what happens is x of t for any t is somewhere between this factor times minus 1 and this factor times plus 1, which are these two enveloping curves that we see here. So 3e to the minus half t cosine of this stuff is a curve that is between those two exponential curves. Since those two exponential curves die off to 0 as t goes to infinity, this oscillating curve in here has amplitudes that also go to 0 as t goes to infinity. We have at our disposal a short MATLAB program that will simulate the damped harmonic motion. Let's run a movie showing a spring undergoing damped harmonic motion. Notice that the amplitude of the swing starts off fairly large and it gets smaller and smaller as it goes on. Let's run that one more time so we can notice that the spring at first stretches and compresses quite a bit, but as time goes on the stretch and compression becomes less and less until we cannot tell whether the spring is moving anymore. So let's run this one more time. Let's look at an example of underdamped motion. A spring is attached to a wall. A mass of 1 kilogram is attached to the other end of that spring, having spring constant K equals 3 newtons per meter. The system is surrounded by fluid, so the damping coefficient C equals 2 newtons per meter per second. The spring is stretched 1 meter from its equilibrium position and released with a speed of minus 2 meters per second towards the wall. Find x of t, the position of the end of the spring relative to the equilibrium position. Assume there is no friction nor gravity. So in our solution, the initial value problem is the differential equation, the mass, which is 1, times the second derivative of x with respect to t, plus the spring constant, which is 2, times dx dt, plus k, which is 3, times x equals 0. The initial position of the spring relative to its equilibrium position, the end of the spring that is x of 0 equals 1, and the initial velocity, x prime of 0, equals minus 2. From looking at this differential equation up here, we can see that the characteristic equation is r squared plus 2r plus 3 equals 0. Using the quadratic formula on this, r equals minus c plus or minus the square root of c squared minus 2mk over 2m. That's going to be minus 2 plus or minus 2 squared minus 4 times 1 times 3 divided by 2 times 1. Inside this square root, the discriminant is 4 minus 12, which is minus 8. The square root of minus 8 is I times the square root of 8. So r then is minus 2 plus or minus I times the square root of 8 divided by 2, and that can be simplified to minus 1 plus or minus I times the square root of 2. So the general solution to the ordinary differential equation is going to be x of t equals e to the minus t times a constant cosine square root of 2 times t plus c2 times sine of the square root of 2 times t. This is a general solution to this differential equation. To solve this initial value problem, we still have to find c1 and c2. So we have seen that the general solution to the differential equation is x of t equals e to the minus t times the quantity, a constant cosine square root of 2 times t, plus another constant sine square root of 2 times t. But we had an initial value problem. We had two initial conditions. X of 0 is 1 and x prime of 0 is minus 2. So let's see, if x of 0 is 1 and here's x of t, just plug in a 0 for the t, and we get e to the minus 0 times c1 cosine square root of 2 times 0 plus c2 sine square root of 2 times 0 equals 1. Cosine of 0 is 1, sine of 0 is 0, so this equation just becomes c sub 1 equals 1. Remember also that e to the minus 0 is 1 here. Okay, now to work with this second initial condition, we have to find x prime of t. X of t is given to us up here, so differentiate it term by term using the chain rule when necessary. So x prime of t is e to the minus e to the minus t, c1 cosine square root of 2t plus c2 sine square root of 2t, plus e to the minus t times the quantity minus square root of 2 c1 sine square root of 2 times t plus c2 square root of 2 cosine square root of 2 times t. Substitute 0 for the t all the way through this equation. Remember, we're trying to fit it to x prime of 0 is minus 2. So substituting 0 into this gives us all of this stuff. But once again, cosine of 0 is 1, sine of 0 is 1. Here and here we also use those facts. So that simplifies eventually to minus 1 plus square root of 2 c2 equals minus 2. This is the initial condition. And solving for c2, we get minus the square root of 2 over 2. So now we know that c1 is 1, c2 is minus the square root of 2 over 2. Substitute that into this formula up here to get the solution to the initial value problem. X of t is e to the minus t times cosine square root of 2t minus square root of 2 over 2 sine square root of 2 times t. So let's summarize what's happening in the four cases in terms of the damping coefficient c. So we have a number line here which represent possible values of c. If c equals 0 right here, the system is undamped. If the value of c is greater than 0 but less than the square root of 4mk, the system is underdamped. If c equals the square root of 4mk, the system is critically damped. And if c is greater than the square root of 4mk, the system is overdamped. So what's going to happen in the rest of this lecture? What is going to transpire from this point on? Well, we're going to consider four initial value problems that are very similar. All of the initial value problems will be of the following form. 2 times the second derivative of x with respect to t plus a constant times dx dt plus 8x equals 0. X of 0 equals minus 1. X prime of 0 equals 1. We'll choose different values of c so that we'll have examples of the four situations that we have described. No damping, underdamping, critical damping, and overdamping. We'll observe animations of three of these spring and mass situations, and we won't see the fourth one for overdamping because, at least graphically, it seems almost indistinguishable from the case of critical damping. So we'll see critical damping, but we will not animate the overdamping. To repeat ourselves a little bit, the undamped situation was the following. we had this differential equation. Notice that there is no term for c times dx dt. There's no damping here. C equals 0. We had the characteristic equation equals this. We solved for r, and we got this quadratic equation in r here. We had two purely imaginary roots, and we found that x of t is cosine square root of k over mt minus a phase shift alpha. So let's look at another example of an undamped system. 2 times the second derivative of x with respect to t plus 8x equals 0. X of 0 equals minus 1. X prime of 0 equals 1. This time, instead of doing the calculation more or less by hand, we're going to use sage math to find the solution for us. So let's see what we can do. Remember that x is a function of t. So first, we will say t is a variable, which we call t. X is a function, x of t. xs0 is just going to be the name of our solution. And DE solve, that's using a differential equation solver built into Sage Math. And then the differential equation, 2 times the second derivative of x with respect to t plus 8 times x, the equals 0 is implied. We're solving for x. We're looking at initial conditions. X of 0 is minus 1. X prime of 0 is 1. So the 0 here corresponds to the zeros we have up here, and then these numbers correspond to these initial values. And then after parentheses semicolon, so our solution is stored in xs0. So we will print the following: the string xs0 equals, comma, and then the value of xs0, and then we will plot xs0 as t goes from 0 to 4, and the size of the figure is pretty small, this small actually, equals 3. So when we execute this code in Sage Math, first we will see the output from this print statement. xs0, our solution, is minus cosine 2t plus 1/2 sine of 2t. That's the solution to our initial value problem. This plot command produces this plot. These were done using Sage Math in a Jupyter notebook. So here we have an animation of undamped motion. We have a spring which is partially compressed, and the length of the spring in its equilibrium position is 6, but at the start of the motion, the initial value, the initial position, is 5. Also, we have an initial velocity of 1 in the positive direction going out this way. Let's run this oscillation. Let's run this animation to see what happens. Here's an example of underdamped motion. 2 times the second derivative of x with respect to t plus 3 dx dt plus 8x equals 0. If you compute the value of c squared minus 4mk, you'll find out that it's negative. The initial conditions are the same as before. The only thing that we changed from the undamped to this underdamped motion problem is this term right here. In the undamped model, this term was missing. In the underdamped model, we have c being 3. So once again, we'll write a Sage Math program very similar to what we had earlier. I'll call this one xs1, DE solve, and then this stuff, twice the second derivative of x with respect to t, plus 3 times the derivative of x with respect to t, plus 8 times x. We're solving for x as a function of t. X of 0 is minus 1, x of 0 is 1. Then we print what xs1 is, and later we plot xs1 where t goes from 0 to 4. We're plotting the solution x of t going from 0 to 4. Figure size equals 3 makes this a small figure. So first of all, here is the output of this print statement, print the solution, and if you look at it carefully, you'll see that it's in the following form: a constant times cosine of, let's say, omega x, plus another constant times sine of omega x, and all of that times e to the minus beta x. And we can see that this starts at -1, the initial condition x of 0 is -1, so the graph of the position starts down here. When t equals 0, x is -1. It goes up and then comes down, and then it comes over here, and it does more oscillations as you go on, but they get smaller and smaller. Okay, so we're going to look at an animation showing underdamped motion of this system. In this top illustration, we have the spring, the mass hooked to the spring, and at 0 we have the wall where the spring is attached. In this animation, we'll see what the motion of this system looks like. Down here is a graph of the displacement of the end of the spring from equilibrium position as a function of time. On the horizontal axis, we're measuring time from 0 through 10. On the vertical axis, we are measuring displacement from equilibrium. So, what do we expect to happen? Well, at time 0, the displacement is -1. The natural length of this spring is 6, so if the displacement is -1, this spring is going to be compressed, and the end of the spring, where it's attached to the mass, should be at 5 initially. Then, as time goes on, the displacement decreases until it's a little bit past 0. 0's right here. So this spring is going to come out this way. Remember, it had an initial velocity of 1, starting at spring position 5 here. So it's going to go out, it's going to pass the equilibrium, and then it's going to come back, overshoot the equilibrium point just slightly, and then settle back towards the equilibrium. Let's run this and see what it looks like. It'll happen fairly fast. So you saw the spring start over here, move out to about, I guess, here, then come back to maybe here, and then come back this way. Let's run it again, just noticing those features. Okay, so notice in this underdamped case, the oscillations do decrease in amplitude. This one was fairly well damped, so the oscillations died out fairly quickly. The amplitude went to 0 pretty fast. Here is the initial value problem for a critically damped system. If we look at this differential equation, c squared minus 4mk is 8 squared minus 4 times 2 times 8, and that happens to equal 0. So the discriminant equals 0 in this case for the characteristic equation. Same initial conditions as we had before. Here we have the program that calculates the solution and prints the solution, very much like the ones we saw before, only we have a different term right here with a coefficient of 8 instead of whatever it was for the other one. And then we will print out XS8, which is the solution, And here it is. XS8 is minus t plus 1 times e to the minus 2 times t power. If you look at this, you'll notice that it's in the following form. X of t is a constant times e to the minus beta t plus a constant times t e to the minus beta t. Here we have the plot command for this solution function, plotting it for t going from 0 to 4 with a small figure again. And here is the figure. As we can see, for this critically damped system, once again, x of 0 is minus 1, so at time 0, the x-coordinate on the vertical axis is at minus 1, and then the curve comes up, and it looks like it might go slightly above the t-axis before it levels off out here. It's kind of hard to tell. We'd have to magnify this to see what's happening. But as we can see, the spring and mass system, the damping, the critical damping, makes the motion disappear very quickly. Let's look at an animation for a critically damped system. Here's the wall, and here's the spring with a mass attached to it. This is going to be an animation, so we'll see what the motion of this is in a few seconds, I guess. Below that is a plot of the displacement x of t versus time t. And x of 0 is minus 1, and as time goes on, the displacement tends towards 0, and it doesn't oscillate at all. So let's play the animation and see what it looks like. So what we saw was that as time went on, the spring, which started off somewhere around here, just slowly approached this, no oscillations whatsoever. This is common in critically damped and overdamped motion. As an example of overdamped motion, let's look at this differential equation with the same initial conditions we saw in the previous examples. With the 9 here for the value of c, this makes this equation an example of an overdamped system. For Sage Math, we'll do exactly the same as before, almost exactly the same as before, except we will have a 9 times the derivative of x with respect to t here. The rest of this is the same as before, except for the name of the function also. When we run this code, we will get that xs9 is equal to all of this stuff, and it's kind of hard to read in that form, so I wrote it again out here. And basically what we have is a constant times e to the minus 1/4 t times this constant minus this constant e to the 1/4 t times this constant. And notice that the square root of 17 minus 9, which occurs here, is a negative number. So this is e to a negative number times x. Over here, square root of 17 plus 9 is a positive number, but we have a negative sign here. And so we have e to the minus a number times t. When we plot this function, it appears like this, the graph. You start at minus 1 at time 0, and you approach equilibrium without, it seems, any local oscillations at all. Notice that this solution is of the form AE to the minus beta 1t plus BE to the minus beta sub 2t, where A, B, and the betas are constants. So what have we done so far in analyzing this spring and mass system? We saw that in every case we were looking at a differential equation of this form, where the mass m, the drag coefficient c, and the spring constant k were all greater than or equal to 0. The mass was greater than 0, k was greater than 0. C here could be 0 or greater. And what we saw was that if C, this is a number line representing values of C, if C is 0, we have undamped motion. If we look at C greater than 0, less than the square root of 4mk, we had an underdamped system. If C equaled the square root of 4mk, we were critically damped, the system was critically damped, and if C is greater than that square root of 4mk, the system is overdamped. So far, we have considered this differential equation and related it to a spring hooked to a mass, hooked to a wall. But the vibrations that we saw, the analysis of motion, can be applied to other situations too, besides just a spring and a mass. But what we had here was a second order linear constant coefficient homogeneous, because there was 0 on this side, ordinary differential equation. The next thing we're going to look at, starting after this lesson, is to solve this differential equation, where f of x is going to be a function that's not identically 0 as it is up here. So this will be a non-homogeneous ordinary differential equation. This will come up when we have an exterior force applied to that mass and spring system, and also in general solving this type of equation is very useful in other situations too. So to solve this equation, there are several different methods that we could use. One way is to somehow change this second order non-homogeneous equation into a higher order constant coefficient homogeneous ordinary differential equation. That is one of the methods that we will see in the near future. I would like to thank you for watching this video. I hope you have found it to be an enjoyable learning experience. If you're interested in ordinary differential equations, there are additional videos in this series covering most of the topics in an introductory course in ODEs. Have a good day.